describe the bond formation of an H2 molecule. In the H2 molecule, there are two atoms which are trying to come close to each other to be stable. For the two atoms to be stable, they should make a covalent bond. So if the atoms are very far from each other, then they are unstable. And if they are closer to each other, they are stable until they make the molecule. But once they make the molecule, they cannot come very close to each other. So if they come very close to each other, the nucleus of them will come closer to each other, and the protons will make repulsion. You don't want the protons to make too much repulsion with each other, so you don't want the atoms to become closer than needed. So they should be close until they make a certain distance, which makes the bond distance, the perfect bond distance between them. Let's make a graph which shows the relationship between the potential energy and the distance. If you want to draw the graph from the beginning, you will see now the atoms are very far from each other. And once they are very far from each other, the potential energy, you can see the distance is too big. So the potential energy is high here. But once you get the atom close to the other atom, they become going to form a bond or a molecule. So they become less stable. And the potential energy as you go down here becomes less, and the distance becomes less until you reach a perfect distance. In this perfect distance, they form the covalent compound, the H2, by joining the two electrons in a shared covalent bond. This is the perfect distance at which the potential energy reaches its minimum value. But if you try to make the atoms even closer, then the repulsion between the protons of the nucleus makes it very difficult. So the atoms start to become unstable again, and the potential energy increases again. As you increase the repulsion and the distance between them decreases, the potential energy starts to grow up again. So you don't want the distance to be very close to each other or very far from each other, because in both cases, the potential energy is high and the molecule is unstable. You want them to be at the perfect distance so that they have the least potential energy between them. So how can I answer such a question? You will tell him, as the two H atoms approach each other, then there is simultaneous attraction between them, and the nuclei of atoms lower their combined potential energy. But at a certain distance, which is the perfect distance, these attractions perfectly balance the repulsion between the closer clouds. You don't want the repulsion to be high, so the potential energy reaches its minimum value here at this bond distance, and the stable molecule is combined, forming the H2. Now let's see the question for drawing the electron dot structure of the covalent compounds. Let's remind ourselves that some facts are very important. These are all covalent bonds. They are all done by sharing electrons, sharing the outermost electrons only. So only you draw the valence electrons or the outermost valence electrons. You don't draw the inside electrons. If you have 2 and 8 and 5 electrons, you don't draw the 8 and the 2, you only draw the 5. If you have 2 and 8 and 7, you only draw the 7 electrons. How do you know the number of valence electrons or the electrons in the outermost shell? It's from the group number. If you have group number 7, you have 7 electrons, 6 electrons, group 5 electrons, and so on. This is very important table, and also how many bonds are needed. If you are with hydrogen, you will make only one covalent bond. So how many covalent bonds you need to do in an element of group 5? 3 bonds, like nitrogen. What about oxygen? Any element in group 6, you form 2 bonds. Any element in group 7, you form only, like chlorine, you form 1 bond. Any element in group 4, like carbon, you form 4 bonds. Every covalent bond is made from 2 electrons. So if you make 1 bond, single bond only, you have 2 electrons, 1 from each side, 1 from each atom. You have 1 bond between 2 H hydrogens, 1 electron from here and 1 electron from here. If you have 2 bonds, then you have 4 electrons, 2 from this side and 2 from this side. Now here you made 1 bond, here you make 2 bonds. If you make 3 covalent bonds, so you are needing to use 3 multiplied 2, so 6 electrons. From this element, you will get 6 electrons, and this element 6 electrons. So you make a triple bond, a triple covalent bond. The most important thing to master is to practice the covalent bond structures and electronic dot structures. Like, for example, H2 is made by 2 atoms of hydrogens. Every one of them share 1 electron. If you make HCl, The H has only 1 electron, and the chlorine has 7 electrons in its outermost shell. It uses one of the 7 electrons to make the bond. How do you know it makes one bond? Because we said anything in group 7 makes one bond. Hydrogen makes one bond also. So they both share 1 electron from each side to form one hydrogen chloride covalent bond. The 6 other electrons are drawn outside. They are not bonding. H2S, you find the central atom. You cannot put the hydrogen at the center, otherwise now it makes 2 bonds. We said the hydrogen makes 1 bond only. You cannot put it here like that also. This is a wrong structure. Because the hydrogen is also in the middle, it makes 2 bonds. So the only correct structure is this one, where the sulfur is in the middle. The sulfur can make 2 bonds because it's in group 6. Any element in group 6 forms 2 covalent bonds. So this is the first bond, and this is the second bond. You can use coins to draw the perfect circles. And then the hydrogen has 1 electron, so it's already bonded with 1 electron from here and 1 electron from here. So you are done for hydrogen, while the sulfur has 6 electrons. Although it has 6 electrons, it makes 2 bonds only. So it uses 2 electrons only, 1 electron to make a bond with this hydrogen and 1 electron to make a bond with this hydrogen. Out of the 6 electrons in the sulfur, because it's in group 6, so it has 6 electrons in the outermost shell, it makes 2 bonds only. So 2 bonds means that it needs 2 electrons, and 4 electrons are unused. You don't draw them outside the overlapped area. Don't draw them in the overlapped area. The overlapped area is where you made the bond. H2O is the same like H2S. 6 electrons, 2 of them are used and 4 are non-used. Group 4, elements like carbon make 4 bonds. Remember that if you are making 4 bonds, it's not necessary they are all given equally or evenly. So for example, a carbon can make 4 bonds with 1 element. It can make 3 with 1 element and 1 with 1 element, or it can make 2 bonds with 2 elements. So this means that the total has to always to be 4 bonds, but you can distribute them like what you want. So CO2, you put the C at the central, the oxygen is on the 2 sides. Why you don't put oxygen in the center? Because if you put oxygen in the center like that, then the carbon will not have enough bonds. If it cannot make 4 bonds here, because if it makes 4 bonds, then oxygen has 5 bonds. So it can make only 1 bond, because oxygen already has 1 bond here, so it has its maximum of 2 bonds, and there is no more atoms to bond the carbon with. What will be this bonded to? When we take the electronegativity later, we will know that the element which is in the middle, the central atom, is usually the less electronegative atom. So C is at the middle, and there is 2 oxygens. This oxygen has 4 electrons non-bonded and 2 bonded, and this has 4 electrons non-bonded and 2 bonded. Other method is to count the total number of electrons. For example, for NH3, it has 3 valence electrons for hydrogen and 5 for the nitrogen, so 8 electrons total. 8 electrons, if you divide them by 2, you have 4 pairs of electrons. The electrons can be bond pair, like between the atoms in the overlap, or non-bonded, which are here. They are not used for bonding. If you have 4 pairs for the ammonia, so the nitrogen is N, 3 of them are used with the hydrogens, and 2 are non-used. So you have a total of 8 electrons. This is 1, 2, and this is 3, 4, and this is 5, 6. And then this is the other electrons. 4. Okay, hybridization is a property which is done by the atoms when they try to make bonding. When this carbon starts to make bonds with the hydrogen atoms in a CH4 molecule, it will face an idea that it needs to make bonds with 4 hydrogen atoms. And that's not an issue, because we now know that the carbon bonds with 4 hydrogen atoms, and the carbon has 4 valency electrons. So it will make 1 electron here, 1 electron here, 1 electron here, 1 electron here. So 4 electrons. And the hydrogen will make, with its 1 electron, 1 bond. So that's fine. So the carbon needs to make 4 equal bonds with 4 hydrogen atoms. 4 hydrogen atoms. But we will face an issue, because let's have a look at the electrons of the carbon that will bond. This carbon atom has an electronic configuration of 1s2, 2s2, 2p2. So it has 2 electrons in the S subshell in the first energy level or first shell, and 2 electrons in the 2s and 2 electrons in the 2p. So they look like that. One is in the px and one is in the py. So this is S, 1s, and this is 2s, and this is 2p. So where are the electrons that will be used to make the bonding? These are the electrons that will be used to make the bonding, 4 electrons. So again, the carbon needs to make 4 bonds. So where are the 4 electrons that will be used to make the 4 bonds? These are the 4 electrons, this one, and this one, and this one. I will notice that these are 4 electrons, but they don't have the same energy. So if you want to make 4 bonds, you will use 1 electron from the 2p orbital, 1 electron from the 2p orbital, 1 electron from the 2s, and 1 electron from the 2s. So these are the 4 electrons that will be used to make bonds with 4 hydrogen atoms, but they don't have equal energy. They have different energy and different shapes. So now I have an issue because this carbon will have an s orbital, which is spherical, to make a bond with this hydrogen, and spherical orbital to make a bond with this hydrogen, and then it has a p-shaped orbital to make with this hydrogen, and p-shaped orbital to make a bond with this hydrogen. These orbitals doesn't have the same shape and doesn't have the same energy, because we know the p orbital has higher energy than the s orbital, and we said we need 4 equal bonds. So how can we solve this issue? We need to make something to make the 4 orbitals, which are 2p and 2s, having the same shape and having the same energy. So finally, when you make bonds with the hydrogen, they will be equivalent bonds. What we are going to do is what's called hybridization. The hybridization, we don't do it scientifically, it's done automatically by the orbitals. So I have 2s orbital, 2s orbital, 2p orbital, and 2p orbital. The name 2s means that it is an s orbital in the second energy level. This is s in second, this is p subshell in the second, and p subshell in the second. So how many orbitals I have? I have 4 orbitals. I want them to change them into 4 orbitals that have the same shape and the same energy, so they can bond with the 4 hydrogen atoms. It's like making a dough. It's like making a bread of a dough. So let's imagine I have 4 pieces of bread. One is spherical like that, one is spherical, one is dumbbell shaped, one is dumbbell shaped, and I want them to have the same shape. So I will just try to mix them into a dough from the beginning. I'll make a dough of bread from the beginning and put them all in one piece of dough, and then try to cut them into 4 equal shapes. Why you are cutting them into 4 equal shapes? So they will have the same energy and the same shape. So let's say I have changed them into a dough, and now I will cut them. So I will cut them into 4 equal shapes. 1, 2, 3, 4. So always remember the number of the hybridized orbitals. What is the hybridized orbitals? The orbitals that have been hybridized or has gone through hybridization is equal to the number of orbitals that I started with. How many orbitals did you start with? 4. 1, 2, 3, 4. And how many orbitals you will end with after hybridization? Also 1, 2, 3, 4. What is the difference before and after hybridization? Before, they have different shapes. You see 2 spherical here and 2 dumbbell shaped here. After hybridization, they are equal shape. So they all have same shape, and they will have the same energy also. Now they will have the same energy and the same shape. So now if you make a bond with the hydrogen atoms will not make an issue. So before, when you tried to make a bond with the hydrogen made an issue, because it said, why this hydrogen is getting an 2s and this is getting 2s, but I am getting a 2p and I am getting a 2p. This problem after hybridization will not be there, because this carbon will make a bond with this hydrogen that's equivalent to this bond and equivalent to this bond and equivalent to this bond. This is very important for the stability, is to have 4 bonds. Now, the last thing to know is what is the names of the new orbitals. Again, the number should be the same, so don't forget, the number should be the same. Number of orbitals before hybridization is 4 and after is the same. The shape before is different, but the shape after hybridization is the same. The energy before is different. This is 2s, small energy, 2p, big energy. The energy after is the same. But what about the naming? What is the name of these orbitals? Before you should give them also the same name. Should give them also the same name. So they are equal here. The name will be given from the name of the original orbitals. Here the name was 2s, 2s, 2p, and 2p. The first orbital has name 2s, the second 2s, the third is 2p, and the fourth is 2p. But we cannot accept that. So the first trick to do is that one of these electrons will be moved, one of these electrons will be moved from here to here. So it will jump. It's like that. This is the orbital. It will jump from here and come here. So it jumped from here to here. To how many orbitals I have now? 1 in the s and 3 in the p. So I have only 1s and 3p. This is 2s, 2p, 2p. So the number of orbitals now is still 4, but the names are different. 2s, again, I have moved one orbital from here into here. Now I have 3p and 1s. So this is s, this is p, this is p, this is p. And again, I have also 3p and 1s. So you started with 2s, 2p, 2p, 2p. What you will end is 4 orbitals. What is the name of these orbitals? I have used how many s orbitals? I have used 1 s orbital. And I have used how many p orbitals? I have used 3 p orbitals. So the name of the new orbital is sp3. And this also will be called sp3. And this is called sp3. And this is called sp3. Why did you call it sp3? Because it started with 1 s and 3 p's. So it's called sp3. How many orbitals I have? 4. You started with 4. You end with 4. The difference is now the name is the same. The names was 2s, 2p, 2p, 2p. The name now is sp3, 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 sp3. And the shape was different. 1 was spherical and 3 was dumbbell shaped, because 1 was s and 3 was p. Now the shape is the same. The shape now is a mix between the spherical and the dumbbell shaped, but it is the same shape. The energy was different. S has small energy and P has big energy. Now the energy is the same for all of them. So now the carbon does not have any problem with bonding with hydrogen. It will join with this hydrogen with an sp orbital, sp3, and sp3, and sp3, and sp3. What is sp3 orbital? It is an orbital which is hybridized. Is this 1 orbital or 4? It is 1. But why it's called sp3? Because it originated from an s and 3 p's.